Hello, I'm Dr. Fran Solomon. I teach environmental biology at Western Washington University, Huxley College of the Environment, near Seattle. My focus is on toxic chemicals, especially endocrine disruptor chemicals. I am passionate about sharing information on this particular topic. This is part one of a 4-part video series. In this lecture, I will explain what endocrine disruptor chemicals are and their mechanism of action, then describe the properties of these chemicals that make them toxic and the sources of these chemicals in the environment. I'll end the lecture by demonstrating and explaining why children and babies are especially vulnerable to the effects of these chemicals. Endocrine disruptor chemicals are a group of toxic chemicals that have recently garnered extensive and increasing attention. A toxic chemical is a chemical that threatens the life or the health of a human or another organism. So when I talk about threats to health, that includes impacts on, for example, activity, growth, metabolism, brain activity, and reproduction. The Endocrine Society defines endocrine disruptor chemical, or EDC, as an exogenous chemical or mixture of chemicals that can interfere with any aspect of hormone action. An exogenous chemical is a chemical that we do not produce inside our bodies. It is a synthetic chemical that is manufactured outside our bodies. Endocrine glands produce hormones. Hormones are chemical messengers that travel from the endocrine gland to a target organ where the hormone brings about some sort of anatomical, physiological, or behavioral response. Some examples of endocrine glands and the hormones that they produce are the thyroid gland that produces thyroxine, the pancreas that produces insulin, the ovaries that produce estrogen, and the testes that produce testosterone. I want to give a shout out to two other lesser known hormones, ghrelin and leptin. Ghrelin is produced by the stomach and pancreas. It's the hormone that tells you you are hungry, and it gives you a message of eat, eat. Come on, eat some more. You want seconds. Come on, you want thirds. Continue eating. This food is good. Leptin is produced by our fatty tissues, and it gives the opposite message. It puts the brakes on what we eat. So it's the hormone that says, enough already, stop, you've eaten enough. In the normal situation, a hormone binds to a receptor on or inside the surface of a cell. This is like a key and lock arrangement in which the hormone is like a key unlocking the cell. And then whatever is supposed to happen does happen. There's some sort of biological or behavioral response, depending on what the hormone is, and everything is fine. However, when an endocrine disruptor chemical is present, it binds to the cell receptor, thereby preventing the hormone from binding. It blocks the hormone. Some EDCs also mimic or act like hormones, thereby causing the cell to respond to that synthetic chemical in the same way as the cell would respond to the natural hormone. For example, some EDCs mimic estrogen. So it's like the EDC is saying to the cell, hi there, I'm estrogen. And the cell will respond to that synthetic, that exogenous chemical in the same way as it would respond to natural estrogen. So whether an EDC blocks a hormone, mimics a hormone, or does both, whatever is supposed to happen does not happen. Instead, what does happen can be quite fascinating, but also alarming and far-reaching. There are more than 1,400 chemicals that are known or suspected to be EDCs. In this 4-part lecture series, I'll be zooming in on 5 different groups or classes: pesticides, flame retardants, bisphenol A, phthalates, and a group of chemicals called PFAS, or the Teflon chemicals. Several properties of EDCs contribute to their toxicity. First, natural hormones are powerful at low concentrations or levels. Concentration and level are synonymous for purposes of this topic. So therefore, chemicals that mimic or block or otherwise disrupt hormones are also powerful at low concentrations. Second, some EDCs dissolve in our fatty tissues. The technical term is lipophilic, which literally means fat-loving. Such EDCs are persistent. This means that they hang out in our bodies for a long period of time. They do not break down, and they are also persistent in the environment, in the air, water, soil, and sediments. Sediments refers to essentially the soil at the bottom of a water body, the substrate, which could be sand, silt, gravel, clay. And then another property of EDCs that contributes to their toxicity is their ability to undergo bioconcentration. This means that the concentration of the EDC in an exposed organism will be higher than the concentration in the surrounding air, water, soil, or sediments. EDCs that are persistent and lipophilic also undergo biomagnification. This refers to the ability of a chemical to increase its concentration as you go up the food chain, so that each predator will have higher concentrations than its prey. So here you see a diagram of a simplified Arctic food chain. Each little green square in the diagram refers to a certain concentration of a hypothetical EDC. So in the lower left corner of the diagram, you see insects. They have just one little green square in them, indicating that the concentration of the EDC is low. However, when the shellfish eat the insects, you see 2 green squares in the shellfish, indicating that the concentration of the EDC will be higher in the shellfish than in the insects. Finfish, such as salmon, trout, halibut, eat the shellfish. You see there are more green squares in the body of the finfish, meaning that the concentration of the EDC is higher in their bodies. Marine mammals such as seals, sea lions, and our beloved but endangered Puget Sound resident orca whales come along, and they eat salmon and other finfish. So you see more green squares indicated in the body of the marine mammals. In this food chain, the polar bear is the top predator. So you see the largest number of green squares in the body of the polar bear, indicating that the polar bear has much higher levels of the EDC in its body than in any of the organisms preceding it in the food chain. Well, we humans are also top predators and are therefore vulnerable to accumulating high levels of EDCs in our bodies via the process of biomagnification. There are many sources of EDCs to the environment. EDCs can be discharged in sewage or industrial waste. Although sewage and industrial waste are treated before discharge, current treatment methods do not totally remove EDCs. So totally legal discharges of sewage and industrial waste can and do contain these chemicals. When it rains on a hard surface, such as a sidewalk or parking lot, if that hard surface has an EDC lying on it, the rainwater will pick up the EDC, transport it into the storm drain. From there, the polluted stormwater flows through stormwater pipes and is discharged to the nearest natural water body, usually without any treatment. EDCs can make their way into the air and can travel in wind currents for hundreds or even thousands of miles from its source, from where they were produced or used, and then end up being deposited in water bodies. Oil spills, big or small, contribute EDCs to water bodies because crude oil is a mixture of many chemicals, many of which are on that list of 1,400 plus that are endocrine disruptors. And then various everyday items that we use in our homes contain EDCs. An important point that I would like all of you to remember is that the impacts of a given EDC on human health and aquatic species are the same regardless of the source of the EDC. There are many ways in which humans are exposed to EDCs. We can inhale them from the air in the form of small particles that can reach deep into our lungs. When we use personal care products that contain EDCs, we apply them to our skin. The chemicals can cross the skin and enter our bloodstream. We are also exposed to EDCs through the water that we drink and through the food that we eat. Babies are exposed to EDCs via the breast milk of their moms. In humans and other mammals, another very unfortunate route of exposure to EDCs is prenatal exposure. It used to be believed that during pregnancy, the placenta would act as a barrier, protecting the developing fetus from any toxic chemicals present in the body of the mother. Well, unfortunately, that is not the case. So we now know that when a woman becomes pregnant, if she has accumulated EDCs in her body during pregnancy, those chemicals will leave her body and will cross the placenta, entering the body of the developing fetus, thereby exposing it 24/7 for potentially up to 9 months. An important point that I would like all of you to remember from this lecture is that EDCs are more toxic to children, babies, and fetuses than they are to we adults. I will explain why. First, a given amount of an EDC will go further in the body of a child or baby because it will be a higher percentage of that child or baby's body weight or body volume. Here are two glasses containing water. The glass with more water represents the body of an adult, while the glass with a smaller amount of water represents the body of a toddler. I have green food coloring here, which represents a hypothetical EDC. So I'm going to add 1 drop of this EDC to the child glass and 1 drop to the adult glass. I will stir up this green food coloring, aka EDC, in each glass, the child glass and the adult glass. And I'll hold up a piece of paper in front of each so you can see that the green food coloring is a deeper green in the child glass, indicating a higher actual dose of the EDC. Let me illustrate with a numerical example. A 70 kilogram adult is exposed to 70 milligrams of an EDC. The dose of the EDC in the body of that adult will be 1 milligram per kilogram body weight. A 14 kilogram toddler is exposed to 70 milligrams of the EDC. The dose in the body of the toddler will be 5 milligrams per kilogram body weight. The toddler weighs 1/5 as much as the adult. Its actual dose will be 5 times greater. There are several other reasons why we need to be most concerned about the exposures of our children and babies to EDCs. First, they have higher breathing and metabolic rates, which leads to faster and greater uptake of EDCs. Second, they're not able to detoxify. We adults have developed mechanisms that enable us to at least partially detoxify some of these chemicals. And finally, children and babies are closer to the ground and put everything in their mouths, hence they have more exposures to EDCs. Part 2 of this lecture series will zoom in on specific groups or classes of EDCs and their impacts on human health. These groups include pesticides, flame retardants, bisphenol A and related compounds, and phthalates. Stay tuned.